So we define a buffer as a solution of weak acid with conjugate base, or weak base with conjugate acid, that can neutralize invading acid or base to keep the pH fairly steady. Understanding the pKa relative to the pH and the Henderson-Hasselbalch equation allowed us to connect to the idea of an ideal buffer, an equal amount of the acid and conjugate base, but also when we may want to make a buffer that has slightly more acid or base. The last term related to our understanding of buffers is buffer capacity. If a buffer is defined as being resistant to pH changes, or a solution that doesn't change pH very much when we add acid or base, we have to think about what that very much means. Eventually, if we keep adding strong acid or strong base to a solution, we will get to a point where we have an excess of hydrogen ions or an excess of hydroxide ions that would make the pH go very high or low. Buffers are defined as buffering, or within their buffer capacity, if they can keep the pH within 1 pH unit of the pKa. When we're thinking about that, we would mean that our pH, wherever we're starting, is going up by 1 or down by 1 based upon adding more strong acid or strong base. But since pH is a log scale, that means that we're really neutralizing a 10-to-1 ratio of strong acid to the amount of base that we have in our solution, or strong base, the amount of acid we have in our buffer solution, that keeps us within our buffer capacity. The first time in these notes that we saw the phrase buffer and buffering is when we were looking at titrations. There was a lot of key features: the initial pH, the pH at the equivalence point. But a key place in all titrations was when we were at the half equivalence point, the pH equal to pKa, and the amount of acid was equal to the amount of conjugate base. Initially, we highlighted all of those features without knowing or recognizing that a solution that has an acid and conjugate base is a buffer. So in a titration involving a weak acid or a weak base, not only are we neutralizing, we are also making a buffer and creating a solution that can buffer for a certain amount of time, or really better said, a certain amount of solution. In doing that, an important thing to note is that we did not go into the chemical storage closet and get, in this case, maybe acetic acid and sodium acetate. We started with just acetic acid. Initially, our pH was fairly low because we had only a weak acid there. The pH jumped up a little bit at first and then leveled off. And the leveling off of a pH corresponds to very little pH change or to buffering. So we made a buffer. And we didn't make a buffer by adding a weak base. We made a buffer by creating a weak base. So this is a little bit different in terms of the way we define or think about getting to a buffer. The example right here shows that if I have acetic acid and I put in sodium hydroxide, that would make sodium acetate. That's the exact same buffer we described in previous videos, acetic acid and sodium acetate. Well, if this reaction goes to completion, our acetic acid would be gone and we'd only have sodium acetate. Before the reaction starts, we don't have any products yet and we only have reactant. We want this reaction to occur in such a way that we're between those two extremes. We don't only have reactants and we don't only have products. We have some reactants and we have some products. And that's when we're at the half equivalence point in terms of a titration, or in terms of just making a buffer, thinking about the stoichiometry and the mole ratio in the right way. So I've color-coded down here some numbers that correspond to the sentences that are described here. If I start with 1 mole of strong base, but 2 moles of weak acid and no products, what would happen here is I would continue to react until my limiting reactant was gone. The purple corresponds to how much goes away. So kind of a connection to a race table, but we're thinking about this in terms of stoichiometry. The acid-base reaction is a one-way reaction. So when 1 mole of this goes away, the reaction has to stop because I now have none of my limiting reactant left. That has made 1 mole of sodium acetate. It's also made an additional mole of water, but we're focusing on our solution here. So we've made a mole of this. We have no sodium hydroxide, and now we have 1 mole of sodium acetate. But because we started with acetic acid as our excess, we had 2 moles of this, 1 mole of it went away, and we still had some left. In this case, if I have a mole of this left and I have made a mole of this, not only have I made a buffer, I've made an ideal buffer. This is kind of the concept that gets us to our half equivalence point, but we can also apply that directly to making a buffer if I have only 1/2 of a conjugate acid-base pair. A very common question. If I have acetic acid but don't have sodium acetate, how can I make a buffer? If I have ammonia but don't have anything with ammonium in it, how can I make a buffer? Remember, any strong acids or strong bases themselves are not buffers, but they can react with something weak to turn it into our conjugate. And when we end with a solution that's a combination of weak acid and its conjugate base, or vice versa, that is a buffer. So acid-base equilibrium as a whole has a lot going on. We've got our definitions of strong and weak. We've got math for strong and weak. We have buffers. We have titration curves. We have indicators. So the key is to really simplify each part of a question to focus in on what is being asked and understand when we're dealing with equilibrium and when we're dealing with stoichiometry.